see. Okay. Action. So let's pick up where we left yesterday. So the last theorem we proved was a metric space is compact if and only if it is what? The condition necessary and sufficient condition. Here. Oh, that's the definition, is it? Definition. What's the theorem? Complete and totally bounded. Okay. Yeah, compactness definition for open cover was for every open cover, there's a not just subcover, right? Finite. Okay. And we show that in metric space, three notions of compactness are equivalent. Limit point compactness, sequential compactness, open cover compactness, they are the same. Okay. So, right. So forward direction was easy because if you assume compactness, you will have sequentially compact, and we have proven that every sequentially compact metric space is totally bounded. And why is it complete? If you look at every Cauchy sequence, what happens to the Cauchy sequence? Since it is sequentially compact, then that sequence will have a convergence subsequence. And you can show that in metric space, every Cauchy sequence with a convergent subsequence should converge and converge the same limit, because limit is unique. The other direction we put more effort that if we assume your space is complete and totally bounded, we want to prove compactness. How do we prove compactness? We just prove sequentially compact. Okay. How to prove sequentially compact? We need to take a sequence and then prove that it has a convergent subsequence. Okay. So remember how we construct this convergent subsequence yesterday. So we start with a given sequence. Okay, we call it x1n. Okay, in particular, you have x11, x12, x13, and so on. Right? Okay, how we take the subsequence of this sequence here? So before we building the convergent subsequence, we consider a particular subsequence of this original sequence here, which is by looking at the ball of radius 1, for example. Right now. Why we look at this kind of ball? Because we want to look at a shrinking radius of ball. Okay, we want to look for a shrinking radius of ball. Because we want to construct what? What do we want to construct? Okay, let me change this notation here. Maybe Z1. Okay, and Z2. What's the nice thing about producing this shrinking ball? Because we want to produce convergent sequence, right? We want to make sure our sequence is Cauchy in particular. Okay. If we can produce a Cauchy sequence, then it should converge. Why? Because we have completeness. Okay, so we want to build Cauchy sequence. So to build Cauchy sequence, what do we need? We need to make sure that the distance between 2 points getting closer to each other. So how do we do this? We will use totally boundedness. Okay, how do we use totally boundedness here? What does totally boundedness give you? For every epsilon, if you consider the epsilon ball, your set can be bounded by finitely many of them. Okay, for any epsilon, okay, how small, you still just need finitely many of them to cover your space. So in particular, we can look at the, first of all, we can look at the ball of radius 1 first. Okay, so how should you imagine this picture here? So let's say you got a x, okay, and you got some sequence like this. 1, 1, 2, 1, so on. Okay. And you consider ball of radius 1 now. Okay, consider ball of radius 1. This, okay, radius 1. So the claim is one of these ball should have infinitely many turns from your sequence. Why? You have infinitely many things, but there's only finitely many balls to contain them. So one of them must have infinitely many terms. Okay, so you make that infinitely many terms into your subsequence. Okay, you make them into a subsequence like x2 1, x2, sorry, x2 2 1, x2 2 2, x2 2 3. Okay, so this is a subsequence x and 1. So on, okay, leading in some ball. Does it make sense? Okay, so meaning if we have this x1 n here, right? Maybe let's say this sequence here converge. Maybe converge. We want to try to converge. There's infinitely many points. Maybe let's say in this last ball here. Okay, so we will make this z1. Okay, this is the ball one of z1 like this. Okay, and then all my subsequence will live inside here, x1, 2, and so on. Does it make sense? Yeah. So all these become my new sequence now, which is a subsequence. Does it make sense? Then we can continue this process. Okay, how do we continue this process? We consider smaller ball. Okay, we consider smaller ball to cover our space. Smaller ball. You can imagine that this process repeat. If you consider smaller ball, but again, you still only need finitely many of them. So meaning one of them should contain infinitely many sequences again. Okay. So in this case here, we will pick x31, okay, x32, x33, and so on. Okay. From where? Of course, from Sn1, but in particular, it is from x2n, sorry, okay, x2n. Okay. From out of these red dot, okay, we pick another orange dot, infinitely many. And then we keep doing this. Okay, we keep doing this. We consider smaller and smaller, keep doing this. Okay. All right. So yesterday, the claim was what? What's the claim? Anyone thought about that claim? About proving the sequence is a Cauchy sequence. So what sequence we are picking here, by the way? We are picking out the diagonal term to form our Cauchy sequence here. Okay, so we'll define, or lastly define y I to be x I I, okay, to be xi is I, and then this is a subsequence of Sn1 in particular. Okay. And then once we can show this is Cauchy, then this subsequence will converge because it is complete. Okay, so we need the goal now is to show yi is Cauchy. Let's show that this is Cauchy. So how do we show that this is Cauchy? So the claim was for every jk, okay, greater or equal to 2n, we can argue that yj and yk is living in the ball of radius 1 over 2n for some center y. Anyone thought about this claim? Is it, do you get anything? Do you understand this claim here? Why? Can you explain to us? Yeah. The smaller ball to be inside the larger ball might not be right. You see, maybe this smaller ball here could maybe make something like this, but it still contain the infinite sequence, right? But the point here is this infinite sequence will still live in the larger ball. Although these two circles might how to say, the smaller circle might not be included in the larger circle, but for sure the infinite terms is included in the larger circle. Okay, so for j and k larger than 2n, okay, for these yj and yk live in what kind of wall? So not that yj live in the ball of some radius 1 over j of some center, let's say zj, and then yk live in some ball of 1 over, let's say, k and zk. Okay, these balls are not living in the ball of radius 1 over 2 and y, but not that by construction, right? By our construction, yj and yk should live in ball of 1 over 2 and y. Okay, by construction. Is that right? So you see, mathematics is like this. When we say by construction, there's like a lot of things happening. But when you explain it, it is by construction, right? Because how do you pick this subsequence here? This subsequence are picking when they are inside all of some radius. And how do you go to the next step? You are picking subsequence again from the terms inside this ball. Okay, maybe maybe our smaller circle doesn't lie completely inside the larger ball. However, the terms that we're picking is definitely all living in the larger ball. That's all what we need because we are just talking about yi. Okay, does it make sense? Okay, no. Okay. Any question? No question? Just ask. Like when you do max, please ask. Okay, follow your just ask. Why follow your heart? Because I want to say you need to train your intuition. And when I teach the first year, I ask them to use intuition. They ask me, "What's intuition?" Then, how to say? Maybe most people when they do maths, it's like I just follow step. I follow recipe. You give me recipe, I do it. Never ask about how the recipe come from. So you don't train your intuition. Okay, please train your intuition. Intuition is very important. This is how we build different branches of maths. So why we study the same thing? Some people use topology, some people use geometry, some people use number. Because these people have a certain form. They like that part of thing. So they want to use that idea to conquer the problems. Okay, yeah. So you need to develop your intuition. So far so good. Okay, now happy. Okay. So this is a Cauchy that followed by yesterday argument using triangle inequality. You can relate the distance between yj and yk to y. So if you pick n large enough by your epsilon, then you can show that um, this yi is Cauchy. Okay, good. So how far have we gone here? So what have we done? We have proved that compact if and only if complete and totally bounded. Okay, so we have a new region here, which is complete. And this works for metric space. Let's use another arrow here. Metric space if and only if complete and totally bounded. That's okay. Okay. Right. So before going to next theorem, I'm going to prove another theorem here. So suppose, let's say, what's the relationship between complete and close? Okay, what's the relationship between complete and close? Can you tell me what's the definition of completeness? Don't ignore me. What's the definition of completeness? Yes, good. Okay, how about close? Hey, since we talk about Cauchy sequence conversion, why not we use a convergent definition for closed? Easier to compare it. So what's the equivalent definition of closed if we want to talk about limit? How's the set being closed? Yes, contain all limit point. So one of them tells you that every Cauchy sequence must converge, and one of you tell that it must contain all the limit points. So how you connect these two? How you connect those two? That's the convergence, what convergence of Cauchy sequence mean, right? And then I mean if you assume that happened, how do you prove that the set has all the limit points, for example? How to prove a set is closed? So let me put down the criteria and let you see if it makes sense or not. So let's go from assuming completeness first, okay? And then we want to show that X is closed. Like what Ziqian said, we want to show that it contains all the limit point. In other words, we need to show that X is equal to the closure of itself, contain all the limit point. And in other words, what this means? What does this mean? If you have a sequence that converge to X, then this X have to live in S. Okay. All right. So how do you use completeness here? So here got a convergence sequence. You have condition of Cauchy sequence. So how convergence sequence and Cauchy sequence relate to each other? Why? You relate convergence sequence and Cauchy sequence. Every convergence sequence is Cauchy. Okay, so you take the convergence sequence here. You see, you take a conversion if Sn in X, Xn converges to X, then you want to show that X is in S. Okay, so you start with a convergence sequence already. Okay, since Xn converges, it's Cauchy. Okay, not the other way around. If it is Cauchy, might not be convergent. This is exactly what happened in rational number. So if it is convergent, then it is Cauchy. So, are we done yet? Are we done? Huh? Not yet. So this is a Cauchy sequence in X. We assume X is what? What do we assume X? S to be. S is complete. This is a Cauchy sequence in X. So this sequence has a limit in S. Okay, yeah. So by completeness of S, Sn has a limit. And it should be the same limit as the original X. Okay, because by the uniqueness limit. Yeah. For question? Question? Feel free to ask. Feel free to ask. We want to show that S is closed. We want to show. We want to show closeness. Okay, yeah. See, yes, okay. You see, very easy confusions come from some very easy misunderstanding. So you just need to fix that. Okay, then you will get things right. Okay, no? Yeah. Everyone okay for this part here? No question? Feel free to ask, huh? Feel free to ask. Okay, the other direction, how do you do? You assume that S is closest. Okay, then you want to show that S is complete. Okay, if you want to show that S is complete, what do you need to start? You need to take any Cauchy sequence. Okay, let's take any Cauchy sequence in S. Okay, does this Cauchy sequence converge or not? Maybe not in S, right? But S is a subset of the complete metric space. So you can view this Cauchy sequence in the larger space X. Okay. Is Cauchy in X. But what do we know about X? Suppose X is a complete metric space. That means what? Xn converge to some limit in X. So you need to ask a question now. Is this X, this limit here, live in S? Why? Does it live in X? Live in X? Snack X? Why? Because it is closed, right? So remember what's closed. If you have any sequence that converges to some limit, this limit need to live in your set. Okay. So since S the snack S is closed, this limit here should live in S. Okay. You see, what's the difference between these two proofs? There's only one direction we really need X to be complete, which is the backward direction here. We only need completeness here. Forward direction only. Meaning what? So forward direction is always true. if you are a subset of some metric space, then S is a complete metric space if X is a complete metric space, then S is closed. Complete implies close, always. But if you want close imply complete, then you need to be a subset of a complete metric space. Okay, does it make sense? So let me add in this new condition here. Close implies what? Sorry, complete imply close is general. But if you want to go from close to complete, you need to live inside a complete metric space because you need the completeness to give you the limit. And you need complete to go the other way. Does that make sense? Okay. So one direction is general metric space. The other direction you need completeness. You need to live inside a complete metric space. Questions so far? Okay. If not, we can draw another corollary here. We have more relation between totally bounded and bounded, complete and closed. So they name this corollary as a generalization of Bolzano-Walsh's theorem. Okay, so what does the Bolzano-Walsh's theorem says? Subset S of a complete metric space. So this is the condition we had just now, right? Okay. This subset is compact if and only if it is closed and totally bounded. So what's the difference between this statement than the first statement we have proven? A metric space is compact if and only if it is complete and totally bounded. What's the difference here? The difference here, we have more restriction on my metric space now. This metric space is complete now. We just only consider subset of complete metric space. Then it is true, it is compact if and only if it is closed and totally bounded. So we replace the word complete with close. Okay, we replace the with close. So how to prove this? So let's say we go forward direction. Okay, let's say we go forward direction. Assume that S is compact. So by the previous theorem, right, there's no condition of metric space. So complete metric space is just one of the metric space. So I can apply. Okay, I can apply. So then S is complete and totally bounded. But does completeness imply close or not? Does completeness imply close? Or no? Yes or no? What we have proven? Completeness implies close, right? For general metric space. Okay. Also, not that. Complete implies close. And from what we have just proven just now. Okay, how about the other direction? So the other direction, we need to assume closed and totally bounded, and then prove that it is compact. So what we need to show? Actually, we need to show that closed totally bounded implies complete totally bounded is good or enough already. Correct? So totally bounded, okay, I already have. But does closed implies complete or not? Why? Yes. So the other direction is true because closed implies complete in the complete metric space. Okay. Okay. So you can see that with the theorem we have just now, okay, it makes this corollary easy. Okay. So this is why sometimes we make lemma before proving a theorem, because it is a small result that you get from the proof. Okay, you can take out the small result, understand the small result, and then you can organize it into a larger proof. Okay, then we'll make your proof cleaner. Okay, this is why we introduce lemma, theorem, proposition, and so on. We split it out. Okay. Okay, good. So this is a generalization of Bolzano-Walsh source. Okay. Cool. What if? What? Let's say. What if we throw away completeness? What result is true? If we throw away this completeness, do we still have if and only if or not? Also not that. Okay, never mind. So if we throw away completeness, what kind of result is true? Okay, what kind of result is true? If we throw away completeness here. Here. So if K is a compact subset of XD, okay, then we can say that K is closed and bounded only. Okay. We have said that K is closed. I mean, let's go back to this picture again. Let's go back to this picture. Let's move this picture down. Let's look a bit closer to this picture here. So far, what do we have? We first prove that for Rn case, the Hein-Borel theorem, we know that compactness if and only if closed and bounded. But in Rn case, the metric space we live in is actually complete as well. And actually, we are using the completeness of Rn there. But if you don't have completeness, what do you need? You need completeness. So that's why compact if and only if complete and totally bounded. Bounded is not enough. Need to be totally bounded. Okay, and then you need completeness. So the Hein-Borel theorem, then the completeness is already built into your Rn. So you don't need completeness there. So you just need closed and bounded. So now we want to investigate how to go from compact to closed and bounded for general metrics. And how do we go about it? So if you use the red arrow line, surely complete will imply close. Okay? Bounded also imply bounded. Okay, you can go forward. Okay, but going backward, you need what? Completeness. Okay, so you can go forward. If a set of compact set inside metric space, then your set have to be closed and bounded. Okay, I don't need to write proof. Just follow this diagram. Okay. Yeah, proof is already hidden when we prove the completeness equivalent between completeness and closed, and also totally bounded and bounded. Does it make sense? Okay. So we can go forward, but we cannot go backward. Going backward, you need what? The purple arrow. The purple arrow says what? You need completeness or Rn. Does it make sense? Okay. So compact imply closed and bounded. So you should ask the question, without completeness, I really cannot come back. If I cannot come back, can I give some counterexample? Okay, so meaning, can you give an example such that it is closed and bounded but not compact? Can you think of an example? a set that is closed and bounded but not compact. I give you 3 minutes and talk with your friend. It's a bit similar how you find the example of bounded doesn't imply totally bounded. Because you want compactness, right? You want finite subcover, right? Think about it. 3 minutes and give you. Try and give an example of closed and bounded. Yeah, the hint is a bit similar to what we had for bounded. Doesn't imply totally bounded case. Yeah. Zhiqian, want to try? Okay, discriminatory. I mean, you don't need to give me space, man. Discriminatory. Space? R space with discriminatory? Okay, let's try. So let's try the attempt with discrete matrix with R space. Surely it's bounded. Is it closed or not? Closed. Why closed? Every point is an isolated point. I mean, the whole set should be closed, right? No, I mean, whether this set is closed or not. The whole set should be open and closed, right? By the definition of the topology or matrix space. Okay, closed in the matrix space is what? That one is for topology, right? Okay, so I mean we need to be a bit careful here, right? So what's this close refer to? This is a close in the matrix space, right? This space contains all its limit points, but all these points are isolated points. Okay. Okay. And then is it compact or not? No. Why? Cannot cover by finite. No, not like that, right? This is compactness, this is not totally bounded. So every which open cover doesn't have a finite subcover? Set off. Okay, so you can see that open ball with radius half doesn't have a finite. This set is closed. Every 2 point is just bounded by distance, say 2, because your distance only needs 0 and 1 in discrete matrix. But it's closed, all of them are isolated. Okay, right. So from this theorem here, right, we can easily deduce our Heim theorem. Okay. Remember that last time when we proved this Heim-Borel theorem, right? What is Heim-Borel theorem? Let me remind you. We didn't give it a name last time. So it just says that if you are compact subset in Rn, if and only if it is closed and bounded. Okay, you can think of your closed interval in R, for example. And we can deduce this theorem from what we have proven. Okay, for example, the previous theorem here give you which direction? This is a backward direction. This is backward direction. How do you go forward? How do you go forward here? Sorry? Yes, R is complete. So since R is complete, you can go from close to complete and then bounded to totally bounded. So complete and totally bounded implies bounded. Okay. So here we are using a bit higher machinery to prove this RM. If not, then we need to use the open cover, then play with the sequence or what, something like that. Okay. So this is a good thing about pure maths. So you can use higher machinery to see lower level theorem. Okay. It's not that you always do this way. This is not true. But it just says that when you go higher level, you should be able to see the low level. Okay. Yeah. So you should go down to see as well. Okay. Not just staying at a high level. Because this is very important when you, especially when you deal with category theory. In category theory, right, we abstract a lot of ideas and introduce a lot of equivalence. If you cannot go onto the ground, see the real equivalence, you will easily get lost inside what they call the abstract nonsense. Okay. You need to be able to go underground, okay. Not just ground, underground. Okay. Yeah. And of course, since once you can deduce this Bolzano-Weierstrass, this Heim-Borel, you can easily deduce the calculus 1 result. Okay, calculus 1 result, which is the Bolzano-Weierstrass theorem, which says that, sorry, not calculus 1, analysis 1 result, says that every bounded in Rn has a convergent. Okay, so how do you do this? How do you do this? What's the proof here? So the proof here, I think I wrote 3 lines here. Let's see, does this make sense or not? So first, given a bounded sequence. Okay. And what can you do with this bounded sequence here? We can consider the closure of set of these set of these sequence term. Okay, the closure of it. I put in the limit. And by this Heim-Borel theorem, S is compact. Okay. You can extract convergent subsequence out of this X. Okay. So you take the closure of the term of this sequence term, then it is closed and bounded. So let's come back here and look for see what's more theorem we had here. So we have, let's say we distinct out this complete condition here. We have another arrow coming from compactness to close and boundedness. Okay, so I think this is the full picture we have for compactness, that comparing with completeness, totally bounded, and then closed and boundedness. Okay. Should be the whole picture that we have proven. Okay. Okay. Right. So any questions so far for compactness chapter here? Compactness to completeness. Actually, we haven't done with completeness. We plan to resume talking about a scholar theorem after we talk about countability and separation. Okay. We'll come back to talk about that because we want to do it in the full generality. Hey, by the way, yesterday I found a very interesting phenomenon from you guys because when I explain something in very detail or very rigorous, you guys seem very. But when I say this proof, I won't prove this proof, you don't feel worried. Oh, this is a bit worrying. Correct, no? Because you're supposed to like how to say ask why something is true. Okay, instead of just listen why is it true. Okay, I mean, yeah, this is what I have to say. I hope you can every time and when people tell you something, try and think why that person say makes sense and then why is it true. Okay, no, does it make sense? And even if I ask you to like read yourself, it's still important. Don't think that it's not in the exam or what. It's not like that. Okay, don't think about exam first. Think about what you learn. Okay, if you learn enough, surely you can do exam one. That's for sure. If and then, if then, if you understand the content well, then you will done good in exam. Not the other way around. If you done good in exam, I don't know whether you understanding the content or not. But if you do bad in the exam, surely you don't understand some of the content. This is for sure also. Okay, so think about this, whether these statements are logically equivalent or not. Okay. To understand the lecture content, you must do good in exam. If you don't do good in exam, then there's not something that you don't understand. Logically equivalent. Okay. So you just need to focus on understanding what is in the lecture content and not focus on the exam. That's all. Okay. All right. Yeah, I still want to comment because you don't worry, I'm quite worried. So I mean, I still want to comment about the thing that we didn't prove last time. I want to direct you how to read my notes when you do your revision. So I think I remember there are two things that I skipped yesterday that I don't prove. So one of them is I didn't prove that any subspace of a totally bounded metric space is totally bounded. Do you remember how I use this theorem here or lemma here? How do I use it? I claim to show a bounded what? Bounded set in Rn is totally bounded. How do I do it? I embed or I see this bounded set as a subset of some totally bounded set, all compact, really. Okay, totally bounded. And then I show that that compact set is totally bounded, and then I show that and using this lemma here, that subspace is also totally bounded. Okay, so I urge you to try and write this down because there's some technical point here that is worth to see. How to prove this is really just following from definition actually. So what's the technical problem here? If you have a totally bounded metric space, meaning what? That metric space you already can bound it by finitely many balls. Okay? But now you want to show that the subspace also can bound by finitely many balls. Can you just use this finitely many ball to cover this subspace or not? Cannot. Surely it can cover, but you need to note that this ball is chosen from where? The metric space X. So meaning the center might not live inside your subspace. So maybe some of the ball is not coming from the subspace. So if you remove this, so the question, if you remove this ball that coming from metric space, can you still use finitely many ball cover your subspace? And the claim here is you can, but how you do it? This is the problem. Okay, how do you do it? Maybe I don't go through this proof with you. I just show you this picture here. So let's say you use a finitely many ball to cover X. So let's say which one? Let me see. It's this one, yellow one. Let's start with the yellow one. Okay, yellow one. And you can see that what space I want to cover? I want to cover this Y. Okay, this Y here. So I use 3 yellow balls to cover. Let's say because it is totally bounded, right? I use 3 yellow balls to bound it. So you can see that where's the center? Can you find the 3 center? X1, S2, S3. So you see X1, S2 is already inside Y. Very good. But S3 live outside it. So this ball is not coming from the center of this ball is not coming from Y. So you see, if I take out this part here, you should ask the question, this part here is not covered. Okay, let me use my laser. So if you take out this yellow ball here, then this part is not covered now. But can you still make a ball that has center in Y, such that you cover this bit? Can or not? The claim here is you can. But how do you do it? Can you still use the same radius of ball to do it or not? Maybe you cannot. But how big enough so that you can cover the uncovered part? The claim here is you use epsilon. 2 times the previous radius is enough. Then you need to show why is it enough to cover. So this is the technical point here. And how to show it? Actually, you just use triangle inequality. So the technical point in this proof is use triangle inequality. Does it make sense? Okay. So in the end, I use a larger 3 ball to cover it. So the larger 3 ball here represented by this pink part. And you see, if I pick this pink part here, this pink open ball actually contains the all open ball that we throw away. This is the result of the proof. Okay, I will include in my lecture note. Please read it. Okay, when you read it, please see if you understand this picture. Okay, yeah. Of course, if you want to show this living inside this ball, you need to use triangle inequalities. Okay, you need to check every point in the old ball. Okay, is living in the new ball. Yeah. And then another thing we didn't prove is this the Lebesgue number lemma. Okay, with sequential compact replacing the compactness. This is still okay if I miss this because I at least show you one of the version. Okay, but still, for the sake of your student, you should learn, right? Okay, why is this true? If I replace sequential compactness with open cover compactness with sequential compact, do I still get the Lebesgue number lemma? What's the Lebesgue number lemma? What is it? What is it? If I give you a open cover, then there exists a delta such that if any subset that has diameter less than this delta, there's some element in the open cover that contains this set. Okay. So in this proof, we use a contradiction. Okay, so you need to try and see why there's a contradiction. So contradiction means what? For every delta, okay, for every delta, you will find some ball that's not living in any of the elements inside your open cover. Okay. So you start from there. There's sequentially compared here. So there's some violation in between. Then try and read the proof and then try and study the picture here. See if it explains the proof. Okay. So please, so as a student, okay, what you need to do, your job is to just understand every lecture content. Okay? Exam is just how to say, it's an indication, okay, on how much you know, how much you still need to learn. Okay, yeah. So just focus on learning as much as possible. So that's why I say if you have questions, so you just ask. Okay, I provide a lot of how to say method for you to approach me. You can go to Moodle and ask. You can ask in Teams. Okay, you can message me also, email me also. Okay. So you have all sort of resources to use. So please use it. Okay, don't be stubborn. Okay, don't say that I want to 靠自己。What is 靠自己？我不是很明白。DIY？OK，只先 say DIY， 靠自己。OK， yeah. Of course, you need to 靠自己 but sometimes people can give you some impetus, right? Can give you some idea, and then you 靠自己啦。I didn't say that I want to like hold your hand and then write your proof. Not like that. Right? Yeah, it's just sometimes you have some confusion. Always is a small confusion that meant once this small confusion turn, everything turn already. Makes sense? Yeah. Okay. So let's take a break and then we'll come back with accountability. Let's break until 12. 至于不见了。可以转变。家具，我不要帮你加附近，点到这么整齐。这跟我们发型师讲剪短，不是剪这样短。每个礼拜四还是。有些理发师的成本不行。 有些理发师我让他剪短啊，他就剪得出我要的东西；有些理发师剪短，他剪出他要的东西。就嗯，
不会买本来想那种拍个这样去年做到很多人很大一点的身上，
很好哎，还是长长的，
因为剪
可以啊。剪多少钱？多少钱？啊，现在你说哎，有些外面10多块。还有那个新开的
但是
片段，
移动看剪到，主要是那个头发 Q 不住啊，剪刀剪的比较好 Q 住啊。
确实，
所以那个是真的，
因为他很长，
那个头发
他适合什么？
剪到，不用行啊，我来，我觉得不错哎，我觉得还买得出，确实这种不错哎。
我觉得他可以换一套砖，
地方肯定没有解释，它的现场是一个，
这种
把它拿过来，我就去，就是
就是已经差不多那种了。
另外一边，然后没有还大一点，
哇，它是上面比较
如果
长，
只是直线的，只是来，
不会吧？我是想说，因为你 open set 的问题是很多那个什么 AN 在旁边嘛，对不对？我现在就拿 close set 哦，
因为你是可以不懂，或者这种东西代别人大，
对，
这样火大不是，
对啊，对啊，对啊，对啊，对啊，
因为那些要拿完全部的 AI，
对啊，对啊，对啊，所以我后来我就拿我 realize 这个 space as intersection，
就它先行在 P 的 complement best 的 action 哦，
不是，我 study 这个 topology as a close set，close
是
set 就是啊，就是我 specify something open instead of specify something open，我 specify something close，其实这样的嘛，因为在那个 discrete 里面，一个 set 里面有几个 is close，所以我 discrete topology 我用 close 的来讲，topology 也可以用 close 的来讲。如果是 close 的话，就比 open 好用了哦，因为 close 的话，arbitrary intersections 还是 close。啊，definition 了，我还没有讲这个东西，我在讲 definition。arbitrary intersection of closed set 不是 close，
是，
对啊，对啊。然后现在我要 realize 这个 z as the arbitrary intersection of closed set。是，嗯，我的想法是你有一串 sequence 嘛，对不对？你一串 sequence 里面，如果你单单看一排的话，对， 就是你有这个 ZP 嘛，对不对？
对。
ZP 如果你分开来看，就是你可以放怎么讲？比如讲你有1、2跟2、1这个点，不对？对不对？比如假设啦，order pair 讲两个先，
OK。
1、2和1这两个点嘛，对不对？所以你要怎样 realize 这个 set of 1、2和2、1？没错，比如说 R cross R，比如说 R cross R 不是 R cross R 这个 set 啊，里面有两个 order pair，一个叫1、2，一个叫2、1。OK，现在我们要 realize 这个 set of 1、2、2、1，我还没有讲完，就 realize 这个 set as a 怎样讲呢？subset of R cross R。OK，那我怎样 realize 呢？我可以把它想成 set of 1、2乘 set of 1、2吗？想一下，可能这个 content 更多东西哦。因为如果想成是1、2乘1、2的话，then 我就会拿到1、2、2、1、1、1个2、2，有就做出更多东西啊。我本来想是这样子，就是我本来要有这两个东西嘛，这样我就把它里面的东西跟它拆开哦。And then 反正 discrete topology 里面你放什么 set 进去都是 open open。then 我就像你讲了，如果我要这个位置有这个东西，then 我就其他放整个 whole space 哦，然后中间就放这个东西。then 我可以 intersect 那两个一起啊，两种东西一起。then 我就有一个 space 哦，cross 一个哦，somehow 好像做出更多东西，还是要 argue 说你的 ZP 是可以这样做出来的，懂不懂意思？就是我把那个 element turn by turn 来看。感觉不可以啦，因为做出太多的东西出来。因为我上网有找过，他们讲 close 的话是用 matrix space 来解释，用它的 matrix 来解释，或者他直接啊，
我是用 matrix 分的嘛。
对，不是，但是是 equivalent，所以意思说它一定有一条路过去，所以你可以了解那个 matrix space 的方法，然后过去 topology，因为 equivalent 嘛，equivalent 嘛，白过来他们好像把这个 point 哦，把这个 ZP 哦 realize 成全部点活在 close unit ball 里面，这个 part 我不知道，他为什么？
这一定是 ball 就 close ball radius one
为什么？
才可以进入。
为什么？我看不出来，直接看从那个 metric 里面，
不难，
不难看。
那会
对呀、如果你要什么？
它确实是一个 close ball。
对，我是想，如果你知道这个东西的话，你应该可以尝试想一下从这里的 close 想去到 topology 的 close 啊。所以你如果是一个 close subset in a matrix space，为什么它 close in topology？连这条路会帮你照你要知道的东西。为什么一个 close set 在 topology 里面是 close in topology？因为我不是很懂那个 matrix 的那个 part，应该那个 part 会解释给你听为什么它会 close 在 topology？因为你要知道 closing topology 的话，你应该要知道 open neighborhood。把这个 open neighborhood 其实就是你 matrix 里面的 open ball。所以你在说它那边 close in a close ball 的时候，应该也是会用到 open ball 的东西。其实我没有错的话，就是 OK。你在说那个 ZP 是一个 close unit ball 的时候，你应该会用到那边 open ball 的东西。可能那个 open ball 在一直长大还是怎么样，我不知道。我 guess 啊，我猜。然后 contain all at limits point 嘛。 limit point 在 matrix space 里面一定是用 open ball 去找的 ，then 你就要放去 topology 那边看一下怎么解。对 ，contain all is limit point 哦，我觉得这个比较合理。我觉得这个比较合理。如果你从那个close unit ball 的角度来，你可能说的这个 set 是 contain all is limit point 比较合理。然后你就去看那个 open ball 怎样 realize as 这些什么 discrete topology 啊 product topology 里面的 open ball，这样你就懂怎样 prove 了。因为我现在是不是很懂那个 metric 发生什么事情呀？那个 metric 给的 open ball 长怎样？And then 这个 open ball 是不是就是那个 discrete topology 加上 product topology 可以给你的东西？有了这两边的 equivalence，应该就会帮你解释为什么 contain 它的 limit point 了啊，很复杂呗。
最开始他先介绍 proposal，讲是 close，他提到没？讲是 close，based on
我知道，我知道，因为确实啊，因为不懂啊，我就卡很久了，所以说现在能不能用另外一条路哦？因为另外一条路已经人家讲了是 close 嘛，可能你用另外一条路看了，你就知道哦为什么可以直接看。因为我现在也找不到，然后我也想不到，所以现在是从知道的东西做起哦。那条路我讲的路肯定是会通的，只是你要知道，嗯，那个 open ball 在 matrix 里面怎样 realize 这个 discrete topology 加上这个 product topology。确实啊，像你讲的，如果他那样子讲的话，应该是可以直接想到的。只是说我现在给一个 possible 的 way 吧，不是讲 only way 啊，就是说，因为我感觉可能你也懂比较多 matrix 的东西，可以 try 这样。当然可能会有一个很快的看法，就很快看到它。但是我想说，就是你如果要很快看到它，你这样子走的时候，应该就会看到那个东西。因为我们现在是从一个不懂的角度去看，不懂我还没有想到。如果我再想到，我再跟你讲啊。
讲到
那个不是 soft 掉了吗？哪一个功能对？
在我那种电脑里面是有分散的，然后后面的全部要后面，
然后
所以如果你在第一个考虑分要我的话，那本身在第二个考虑分后面的摆两边，把后面的那些全部都要是整个的。
然后
但有时候，如果在第一个考虑分后面全部要 A 的，那你在后面全部是肯定不行。
那你写下来看，
OK，
你写下来，你写下来。Okay, let's continue. Ability. So what are we counting here? Okay, so we say that a topological space, okay, is said to have a countable basis. Okay, so countable basis here means what? The point means if there is a countable collection or countable set P. Okay, so what are the things inside this set here? These are the open neighborhood of X. Okay, so meaning open set that contains S. Okay, so what does this collection have to do now? Okay, so for every open neighborhood of X must contain at least one of the elements of it. Okay. Can you imagine what this is saying here? If I say that this point, okay, of the topological space has countable bases, what does it mean? It means that for any neighborhood around that V, you can find one basis element. This basis element is not random basis element. Right? This basis element, okay, we cannot quite call it a basis element, right? Because it might be confused with the basis element that generate the topology. It's just a collection of open neighborhood of X, okay? And then inside that there's countably many choice you can do. And the random neighborhood of X should contain at least one of your element of the choice you make be the countable choice. Does that make sense? Okay, later we'll see example why what kind of uh, base have this kind of property. Sorry.
This checks only for F. For one point.
Yes, because we are talking about countable bases. Or can you now think of one example in your mind or not? When you think of countable, right, you should go for like n. So how you index n and then so that can do this job. Maybe we just go for, let's say R, for example. Okay, maybe say pick a point. Let's check whether it's true or not. Maybe pick 1. Usually we pick 0. We like 0 almost. Because anything minus 0 is itself. And so you ask the question whether there's a countable basis here or not. Okay. What does this countable basis have to do? So our open neighborhood here is open interval, right? Okay. So any open interval around x equals 0, you need to be able to find one element from your countable list. It's open example. Can you do that? Okay, so what's your countable list you want to put in? Sorry? Minus 1 over 2? Minus 1 over n. The radius is. Oh, you give me an interval, is it? Okay, what's the interval? Minus 1 over n to 1 over n. Yes, right. So this is what? This is exactly the ball of radius 1 over n around 0. Okay, for all. Particular, this set is countable, right? Sure. Okay, good. So next thing you need to check is whether for every open U that contains 0, U will contain some element in B or not. Is it true? 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 True or not? Simple say true. Why is it true? You're a mathematician, right? You need to prove. This is why we learn analysis. So how to prove? Sorry? Since U is open, right? Then last time we prove what? U is a countable union of open interval, disjoint open interval. Okay, so we can write U equals to A1, for example. So we're really precise. So maybe AI, BI, okay, or some AI, BI. But we know that 0 live inside the set, right? So since, okay, AI, BI disjoint, okay, this is a very important point. So that we know that there is a J such that 0 is living in one of the AJ, BJ. Okay. Okay. So we already identified that 0 will live in one open interval here. So can we find a ball such that this open interval here will contain any ball? How do we pick this n here? Minimum of AJ and BJ. And then we can use Archimedean property to pick this n. Yeah, so we have 0 here, AJ here, BJ here, for example. Okay, so we want to pick the minimum of the two. Okay, minimum of the two. And then we can pick a 1 over n that is inside there. Okay, makes sense? Okay. Okay. So we pick n to be larger than 1 over minimum of of AJ and BJ. Make sense? Okay, no? No question? So far, so good? Okay, right. Okay, good. Next, so what if we can do this for every point? I think this is what we can do for R. We can do it for every point, right? This countable collection thingy. So we will say that this space is first countable. Okay, so if a space has countable bases at each point, okay, at each of its point, then this X here will satisfy the first, countability axiom. Or simply we just say that it is first countable. Say that it is first countable. To be first countable. Okay, so if you can do it for every point, then we'll call the space first countable. For example, not just R is first countable. Actually, every metric space is first countable. Every metric space. Is it true or not? Every metric space is countable. You use the same collection. Okay, at every point you consider the ball of radius 1 over n. At every metric space you can do that. You can form that ball. And let's see what time is it? 12:39. So another example is, so I'll give you one example. Not just R is first countable, actually every space is first countable. So this is similar to the case of similar to the case of R. Okay. You just pick ball of radius 1/n. And one can show that R with cofinite topology is not countable. One can show that this is not first countable. So how to show this? One have to go through by contradiction. Right? Suppose you can do first countable. And then you will deduce that R is countable. Then you have a contradiction. I'll leave this proof inside my notes. Okay. So the idea is you suppose that R with cofinite topology is first countable. So meaning at every point you would have countable collection such that any open neighborhood around that point you can find elements that contain inside this open interval. And then you will deduce that R is countable. Then you have a contradiction because R is uncountable. Okay, I will leave it inside my notes for this proof here. So if you don't understand, we can discuss it again next lecture. Okay, please have a read. So a very good property that we want to look at instead here is let's take a topological space. If you look at a subset of it and say that if sequence Sn, okay, of a point in A converging to X, then X is in A bar. Is this obvious or not? I think this is almost definition, right? Okay. But what is true is if you are in the A bar, okay, and the space is first countable, then the converse will hold. Okay. The converse will hold if X is first countable. So meaning if your space is first countable, I can create a sequence that converge to limit point. Okay. If your space is first countable. So meaning at every point you have these countable bases. Then we can create a sequence that converts to your limit point. Okay. And D. Is let F be a map. Okay, if this F is continuous, then for every convergence sequence in X, then Fxn converge to Fx. This is true, right? This is just continuity. Okay. But the converse is true if converse wrong. So the converse hold if X is first countable. Okay. All right, so I think we will just focus on proving the converse now. Okay. Proving the converse. So let's prove the converse. So in both cases, we need to assume X is first countable. Okay, so for the first one, what do we need to prove? We need to prove that if X is in the closure of A, we want to create a sequence that converges to S. So how should we create this sequence here? We create this sequence here. When converging, right? So last lecture, how do we do this? We consider a shrinking radius of ball. Okay, but in this case here, since S is first countable, what can we do? What can we do? Can we straight away consider a neighborhood of radius D? So here is a topological space, right? If it is a metric space, we can do it. How about topological space? Any idea? If metric space can, but because metric space, the countable collection we can get is the shrinking ball. But how about topological space? I mean, what's the definition of convergence here in topological space? Convergence really? Yeah. Every neighborhood. Okay, so for every open neighborhood, there exists an n such as Sn great in U. And then if you are limit point, what happens? So if it's in the closure, then you are one of the limit point or you are already in A. If you are a limit point, then every open neighborhood of X intersect A in some other point other than X itself. Okay, so this is what you have. But you need to create a convergent sequence. So meaning the Xn you pick, you need to show that for every open neighborhood of U of X, there is some n such that Xn is in U. Okay, so how do you go from the first one to the second? By first countable. So first countability tells you what? For every point in X, wherever in X, you can find a countable collection of open set that contain that point, such that for every open set of that set or containing that point, one of the element inside of collection will be subset of that open set. So how to use that condition to create this sequence here? We try and prove it. I also don't have proof in my notes. Wait. So how we start? So we start from let's do it here. So we start from X in A bar, right? Okay, and then so we can consider one of the neighborhood, is it? 要做，Are we proving the same thing? 可以，老庄，我没有要 prove first countable，我要用 first countable。Yeah, yes. No. We prove A first. So if X is in the A bar, then there is this sequence in Xn converge to X in A bar. Next. Okay, so we first suppose X in A bar, right? Okay, and then because it is a limit point, right? So in the yes, so two cases. Okay. If x is already in A, then you can simply take constant sequence of x, right? Okay. So now suppose x is in the is a limit point of A. Okay. So if x is in A, we can take constant. Okay. So now suppose x is of A. Okay. So if I suppose x is a limit point of A, meaning we have this definition here. Every neighborhood of x will intersect some other point. So what can we do here? Also, we have another theorem, right? Every open neighborhood actually contains infinitely many points. Okay, so we're trying to use this property to build our SN. So how to build SN? How to build SN? Any idea? So then how do you want to say it? Make different stuff or the same stuff? Mm-hmm. Okay, you mean you want to start with the countable collection, is it? Okay, so since A is first countable at x, you consider the first countability at x at this limit point here. Okay, then we have a countable collection, right? B, let's say we have B1, B2, B3, and so on. Okay, so what do you want to do with this B here? Use the limit property, limit point property. So you say that in B1, so you can pick x1 from B1 such that it is not x. Is it like that? This is what you want to do. Okay, and then S1, S2 is in B1 intersect B2, but not in X, like this. But how do you know that B1, B2, the intersection is not empty? How do you know that it's not empty? Don't know. Wait, why you say don't know, then you ask people go and do it? I mean, okay, so go back to first countability, right? It says that every open neighborhood of V must contain some element from this B, right? So meaning these B1, B2, B3 are also a random neighborhood for V. So meaning these B1, B2, B3 must at least contain some or one of the other B1, B2. So that's how to say. So how to say this? So instead of B1 intersect B2, right? maybe you can take B1 intercept with some Bj. Correct or not? Some Bj. This J will depend on what? Understand or not? Don't understand. Okay, good. Come back to the definition. What does this collection of B do? For every neighborhood of X, that at least one element is sitting inside that neighborhood. But in particular, this B1 is one of the neighborhood. So meaning there will be other elements sitting inside here. But this element could be B1. Then, sorry. I mean, it could be B1 or then there's nothing to play around here. Right? Then we could just keep getting B1 later. You get what I mean? So let's go back to this definition. Did we miss anything or not? For every open neighborhood of X contain at least one of the element in B. Yeah. If you just pick B1, sorry.
At least containing X, so you don't be.
Yes, 你讲吧。
所以
Sure. Next option.
这条 X 也是吧？
Okay. Okay, makes sense. Okay, so let's come back again. Wait on. So if we continue, like, okay, let's go back to your construction. So what's the construction here? Because V1 is an open neighborhood of X, so X is a limit point, so that means B1 has infinitely many points. And then B2 also has infinitely many points.
Something other than X bar， 可能就会有在
A. Let me think. So I mean, you need to consider not just B1, is it? So you need to consider. Oh, okay. So I think one thing we miss is this B1 is in A. I think one is in A intercept. And now let me think. Where's this set here? X is in the BB. Okay. So you say that actually we need to include X and X. Something like. I mean, does the two infinite terms must agree or not? That's my point. Can the two infinite points be different? I think you mean this is it. This intersection here should contain some other BJ. 可以 right? 可以 right? I think this one makes sense, right? 可以 right? You take B1 intercept B2, but this is another open neighborhood living in that of X. You containing another element from this countable collection. Okay, and then you don't want to pick the one that you picked before, and then you pick that one. Okay. Okay. Makes sense. Then we keep continue this. You can keep taking this intersection here. So what's this intersection here? What's the next step? B1 intercept B2 intercept B3 intercept Bj. Is it? No. You go B3 and then go BJ. Correct. And then there's some other B. Let's say this one is BJ1, this one BJ2. You pick S3, and then you don't want to pick anything out of second. Like this. Okay. Yeah. You mean just simply take BJ1 with B3? Huh? 一样或不一样？BJ1 should contain the X. Oh, I think what you mean. So you mean 不要把这个放进来是 so such that X2 is not here like this. And like that, such that X3 is not what we have chosen before. Like that. Okay. This one make more sense or not? Okay. And then what? Then what do you need to show? Then you need to show that this sequence converges to X. Why? To make a neighborhood. So you need to take any neighborhood of U. Okay. And then this neighborhood of U should contain one of the B, J. And then, so for all the sequence after the BJ, right? Because we are now taking the intersection. Then there's all this sequence here should live inside this B and or BJ. Yeah. Does it make sense? Make sense or not? So how to find this capital N here is to find it using the first countability property. And by the choice we make here, all the xn or sj greater than n, it will live inside where? Inside B and or B, yeah, Bn, for example. Okay. And then this Bn here is living in any neighborhood that you give me. You give me a neighborhood, the first countability give you an n, and then by our construction, all the sj greater than n live inside Bn. Sense? Okay. Okay. Some question before we finish? Okay. Try and write out, and I will write it out, and we can check. Okay. Yeah. Yes. Yes.
The U-cycle, every step is finite, right? But
For any step.
yeah. Finally, we're going to take all the B.
Maybe, yeah.
So it's
not necessarily open. But we are not considered infinity. So each step is finite. Yeah, each step is finite. That's okay. Yeah, each step is finite. We are not considered like this. Not like this. Just each step is finite. Yeah, good point. Yeah, but every Sj is living in a finite intersection. Okay. Okay, so next time we'll prove more theorem, and then we will go separation. So question? Any more last question? Question or not?